Hey Blue Devils, today we're going to talk about sound. So what is sound? Have you ever thought about that? I think sound is one of those things we've just experienced our whole lives, and yeah, we kind of know what it is, but do we know what it is? Do we know why it happens? How it works? So when I ask this question in class, I usually get an answer, well, it's a vibration. Well, what's vibrating though? Okay, so not all vibrations are sounds, but they can create sound. So we're going to look at that today. All right, the first thing we're going to do is look at what I think is a simple example of something that makes sound is a speaker. So speaker, like you have hooked up to a radio or something like that, sound comes out of the speaker, right? Well, what does that mean? Sound comes out of the speaker. So let's take a look at a video clip here. Okay, so here's a little video clip of a speaker I found on YouTube. I just searched for a slow motion video of a speaker and found this one. The author is saying that his camera is shooting 900 FPS, 900 frames per second. So that means every second the camera is taking 900 pictures. And that's all a video is. It's a series of still images that go by so quickly that we perceive it as a video. Like your cell phone camera might be, you might have a 60 frame per second, but probably not much higher than that. So this is 900 frames per second. So let's take a look at this. Okay, here we go. All right, there we go. All right, so right there is 900 frames per second. You see the speakers just oscillating in and out like that. That's all a speaker does. It vibrates in and out. So you need air for this to work. So the air molecules right in front of the speaker, when the speaker is coming at it, it compresses those air molecules. It makes a high pressure region right there. And then when the speaker goes back into the case, it's creating a lower pressure region right there. And that's a sound wave. It's just alternating high and low pressure. That's it. So here's an image, and I'll put links to these images. I found them all on the internet. So this is like a speaker. So this red plunger is moving back and forth. So it compresses the air molecules, making an area high pressure, and then when it moves up backwards, it's making an area of low pressure. So you remember from chemistry or another class, atmospheric pressure, so about 14.7 pounds per square inch, or 101 pascals, if you remember that. So that's what we're experiencing right now. Right now, as you're watching this video, you have pressure on you. It's 1 atmosphere. Our bodies are used to it. So any increase in that, you've got high pressure. Any decrease in that, you've got low pressure. So this image also does a good job of showing the lack of a bulk movement. We talk about waves, there's no bulk movement of the medium. So we've got the 3 red dots here. These represent one of these air molecules. So the black ones, they get all mixed together. You can't keep track. So they've highlighted 3 of these as red. You see they are not moving across the screen like that. They're just oscillating back and forth. There's no bulk movement. Down here we can plot the pressure. So we've got atmospheric pressure, we've got high pressure, that's the compression, and we've got the low pressure, that's called rarefaction. We'll see that word in a minute. And then the wavelength is measured just from one high pressure to the next, or it could be one low pressure to the next. It's all the same. Amplitude is something that we don't see here, but amplitude, if this moved back and forth more than it is, you'd have even higher pressure here, even lower pressure there, so you get a bigger amplitude here. All right, so let's look at some properties of tuning forks here. So this is a similar concept. So it's just compressing the air. It's decompressing it, so high density, low density, just kind of the same topic there. Here's another image showing pretty much the same thing. High pressure, which is called compression, low pressure, which is rarefaction. So the tuning fork, when it's going to the right in this case, is creating that high pressure, that compression. When it goes to the left, it's creating that rarefaction. And then again, we see it plotted as a pressure with atmospheric pressure at equilibrium. We've got compression, we've got rarefaction. I do want to point out that we're going to see that sound waves are longitudinal. This does look transverse. Don't let that confuse you. It's just a way of plotting the pressure on that. Okay, so here we go. It's a longitudinal wave. That means the particles move parallel to the wave motion. Those molecules were moving back and forth as the wave was going across the screen like that. Whereas a transverse wave, particles move perpendicular to the wave motion. It's not what we have here. It's longitudinal. Sound waves are mechanical, which means they need a medium, which means you would not be able to hear sounds in a vacuum. So you go out into space, you would not be able to hear sounds. You need a medium. Usually, you know, the medium we're used to here is air. So that's the medium you're hearing sound right now is through the air. But sound can travel through solids and liquids and other gases besides air as well. So it's not just those. Amplitude is proportional to loudness and the energy. You've got a bigger high pressure, a smaller low pressure. That's a bigger amplitude. That's going to develop. It's going to result in a louder sound. And frequency is the pitch. Okay, higher frequency, lower frequency. That's the pitch of the sound. So human hearing generally is accepted as 20 hertz to 20,000 hertz. Now, 20,000 hertz, not everybody can hear that high. I can't. The maximum I can hear is around 14, maybe 15,000 hertz. So it depends person to person, but that's the accepted range. And then sounds above that 20,000 hertz, that really high pitch, those are called ultrasonic sounds. So like a dog whistle is just a frequency higher than 20,000 hertz because dogs can hear frequencies higher than that. Ultrasound, like for babies, you know, what the doctors do to get an image of the baby, that's ultrasound. It's sending a sound wave into the mom's abdomen area. That sound gets reflected back and it creates an image. That's another topic, but that's at a very high frequency that we cannot hear. Okay, so now we're going to move on. My daughter and I decided to go outside and measure the speed of sound. To measure the speed of sound, we needed a pretty good distance between us. So we went out to the field, or the little open area by our house. Now, this is my daughter Emily. She's way down there. You can see how blurry she is. So a couple of limitations in this experiment. One was the camera we're using, my cell phone. So I did this in 60 frames per second, but it doesn't have a great zoom on it. So that's why she's kind of blurry down at that end. The other thing, it was a little windy today when we did this, so that can affect the speed of sound as well. So I need to see her and I need to be able to hear the sound. So why we need the big distance is we're taking advantage of the fact that sound moves a lot slower than light. So a great example is fireworks. You've all seen fireworks before, and you see the explosion, and then sometime later, could be 5-6 seconds even, you hear it. So there's that delay between what you see and what you hear. Light moves so fast that for these purposes, it's instantaneous. It's technically not, but it goes so fast that we can consider it that. And then the sound, we have a delay there. Okay, so I'm just going to play a little bit of this so you can see what we're dealing with. I don't know how well the sound is going to come through, so I'm not going to spend too long on it. Okay, so I have her with two pieces of wood, 2 blocks of wood, and she's hitting them against each other over her head. So you can kind of see her doing that, and then you can hear the sound a little delayed on that. And the wind was kind of affecting the sound on the video as well. Okay, so you can kind of see what we're doing there. All right, so it collected the video and audio tracks. I'm not going to go through this, but basically we've got the frame counter right here. So like I said, it's 60 frames per second. So if I just tab through this one at a time, you can see that just adjusting by 1. And then we go to 59 because every second it resets at 0, just kind of like a clock. So it's 60 frames per second. But that's how I'm going to get the time from this using that counter. Now, So I don't know if you noticed, she was hitting them together two different ways, really hard and then a little bit lighter. So we wanted to hear a volume difference in that to see if the volume affects the speed of sound. And then we also want to see if frequency affected the speed of sound as well. So now here you're going to notice she's a little closer. I'll explain that in a minute. But let's play this so you can kind of hear what we were doing. UPS. Okay, I hope you can hear. The wind's picking up. Let me go over here. Okay, so hopefully you heard two different frequencies in there. So again, we were just testing to see if frequency would affect the speed. Okay, now one thing, I'll explain this right now, with the 50 meter distance, so I was having trouble hearing those tones. We just had a Bluetooth speaker hooked up to a cell phone to create those tones. I was having trouble hearing them when I was way far back at 115 meters it was. So I had to move into 50 meters. The frequency one is not very accurate at all because there was a delay from when she pressed the button to when the sound started, and with her hand coming down to indicate the start, it's like, where in that was it actually starting? I don't know. So the one thing I did get out of this though is the results were fairly consistent. All right, so we can still compare the two frequencies, but we're not going to get actual speeds from them necessarily. We'll get the speeds from the blocks of wood clanking together. Okay, so let's move on and look at how we're going to solve for the speed here. Okay, the first thing we're going to look at is how the loudness affected the speed. All right, so the camera was set to record 50 frames per second, which means every second it takes 60 pictures, so it takes 1/60th of a second for each picture. In other words, there's 1/60th of a second between each picture, so a very small amount of time. Both the loud and the quiet sounds, I went through and I was able to see it fairly well, I guess, but both the loud and the quiet sounds took 21 frames to travel 115 meters. So in that first clip, when she was knocking the blocks of wood together, I checked out what frame we were on when it visually looked like those blocks were coming together, and then I checked what frame we're on when I first heard the sound from them, and it took 21 frames. By the way, on the original file, I could see it a little more clear than what was shown on the video, but so it was, I felt pretty comfortable with that 21 frames. So because it took them the same number of frames, that means it took them the same amount of time. The loud sound, the quiet sound took the same amount of time to travel the same distance. So my conclusion, that amplitude or the volume did not affect the speed of sound. All right, so then we looked at frequency. So again, cameras had the same setting, so 1/60 of a second between pictures. The distance, like I said in the video or a minute ago, was 50 meters. So I'm not going to use that to calculate speed, but the results were consistent, it seemed, from one hit to the next. So first with the 400 hertz tone, that took about 20 frames for the sound to get to me. So if you compare it to at 115 meters, you're probably thinking, oh, that's about the same. No, disregard this data. We can compare these two frequencies, but that's all we can really do with that. So the 400 hertz took 20 frames to get to me. 4,000 hertz. The 2,000 hertz took 22 frames to get to me. That's pretty much the same. Okay, so 2 frames, 2/60ths of a second, 1/30th of a second. It's a very small amount of time frame there. So just in the margin of error with Emily's hand coming down, when did the sound start? I think if we were to see a difference, I mean, we have half the frequency there. If we were to see a difference, it would be significant. It would be noticeable. So frequency is not going to affect the speed of sound in air. Now, one thing I think that makes sense. I've never thought about it this way before, but so what we were playing in the video was a single frequency, a pure tone, so to speak. Well, pretty much every sound you hear on a daily basis, somebody's voice, a car horn, whatever, that's a combination of a lot of different frequencies. So think about this. If somebody's talking to you and their voice has a lot of different frequencies, if frequency affected the speed, you would hear, one frequency and then another frequency and then another frequency. It would be a mess, but you get them all at the same time. So I think that's further evidence that the frequency is not affecting the speed of sound. Okay, so we're going to do the calculation here. So I'm going to use 21 frames per second. That's about what we're seeing with the blocks of wood. So at 60 frames per second, for 21 frames, that would take 0.35 seconds for that sound to get to me. We know speed is distance divided by the time it takes to travel that distance. So we did have 115 meters divided by the 0.35 seconds. So there we go. Speed of sound calculated 329 meters per second. Now, the speed of sound does depend on temperature. Okay, and it's given by this equation. 331 times the square root of TK, that's temperature in Kelvin. You guys remember that? There we go, absolute temperature in Kelvin, divided by 273. So here's the conversions. Kelvin and Celsius, they're just 273 different. So if you remember, absolute zero is 0 Kelvin. That's actually minus 273 degrees Celsius. So they're just offset by 273 degrees. So 0 degrees Celsius is 273 Kelvin. And then to get that conversion, because we're in America and we use Fahrenheit, the conversion between Celsius and Fahrenheit, we have that equation. So we're going to use those equations to calculate the temperature of the air. Okay, so we calculated 329 meters per second, so I put that in. For the speed, I'm going to solve for the temperature in Kelvin, 269.7. I'm going to convert that to Celsius using that 273 value. So Celsius minus 3.3 degrees Celsius. Okay, we know water freezes at 0 degrees Celsius, so that sounds kind of reasonable. Converting that to Fahrenheit, we get 26.1 degrees Fahrenheit. Makes sense. It was kind of a cold day today. I measured the actual temperature, 37 degrees Fahrenheit. So we're off by about 11 degrees. Okay, sounds like a lot. However, if we use 20 frames instead of 21, just one frame different, 1/60th of a second different, look at the difference it makes. The speed would have been 345 instead of 329. Our temperature would have been nice today, 74 degrees instead of 26. So there's the limitation in the 60 frames per second even. A camera with a higher, we'll say shutter speed, the frames per second, you could get that probably a little bit better there. Okay. All right, how about speed of sound in media other than air? Okay, so we've got solids, liquids, and gases. Sound can travel through all of those, can travel through a sound, piece of metal or something like that, or earth, can travel through liquid like water, can travel through a gas like air, okay, or any other gas. So next, we're going to look at a video I found on YouTube of an experiment where they tested, they didn't do liquid, but they did solid and gas. So they did earth and air. Now it's kind of a weird video. They have an explosion set to go off, and one person is wearing a blindfold, so they can't see anything, but they can hear it. One person has their eyes, unblocked, so they can see when that explosion occurs. And then the third person, this is the weird one, they've got a blindfold on so they can't see it. They also have ear protection on so they can't hear it. And they've driven a piece of metal rebar into the ground. And the person actually has their teeth on that metal rebar. That's the weird part. But they can feel the vibrations there. And a vibration, that's just the sound wave traveling through Earth. Okay, so let's take a look at this video.
So, who's going to be the first, second and third to detect the explosion? They were waiting to see the light, hear the sound, or feel the sound. Samantha was first because the light got to them before the sound. Elizabeth was next when she felt the sound coming through the ground. And Fung was last when he heard the sound of the explosion coming through the air. The speed of sound in the air is 350 meters per second. At 5,000 meters per second, sound travels much faster through the ground. But light is much faster than any sound, at 300 million meters per second.
Okay, so we saw that it traveled the fastest through the ground, and then next was through the air. So here's a table I got from a textbook, just general idea of the speed of sound through different media. So the top part, we have the gases, so air, 0 degrees Celsius is that 331, 100 degrees Celsius, so we can see that the speed is faster at a higher temperature. We saw that in the equation. Other gases here. Liquids, you can see, in the thousands in terms of meters per second for their speed. Now you notice there is a little overlap. Hydrogen speed, sound moves pretty fast in hydrogen. So it kind of overlaps with the liquids here. So generally, gases, the sound is the slowest in gases. And generally sound is fastest in solids, and you see there's a little overlap here. Vulcanized rubber, that doesn't transmit sound very quickly at all. But you see like these metals, look how fast that is, okay? So back to the temperature. Why do you suppose warmer air sound travels faster than in colder air? Okay, well, when you heat something up, the molecules are moving faster. And that's a key there, okay? So they're able to bump into the next molecules more quickly than when they're colder, because remember, that's what a sound wave does. It's just kind of like a domino effect, molecules bumping into each other, and then that's how it progresses. You don't have the bulk movement of the medium. They just bump into each other and move on like that. So now the question is, why is sound fastest in solids and slowest in gases? Okay, I ask my classes this all the time, and usually they have it completely reversed. Usually they say sound is fastest in a gas and slowest in a solid. Okay, well, I put my other daughter to work today to set up this demonstration. Okay, so these are dominoes just set up on end, so we're looking down from above, and here the dominoes are closer together, here the dominoes are farther away. Okay, between a solid and a gas, which row of dominoes do you think is which? Okay, so solids are more dense than gases, so their molecules are closer together. So this bottom row would kind of represent the solids. The top row, gases, the molecules are farther, they're spread apart farther. So that top row represents the gases. All right. So now again, this is just a loose analogy, but it shows it fairly well. So let's watch. I filmed this in slow motion. Okay, did you see which one got there first? All right, I can replay that again. Oops. Okay, so both lines were the same length to start with, but the bottom row got to the end first. Okay, so with solid materials, the molecules are closer together and there's a much stronger interaction between them. As soon as one vibrates, that next one feels it and moves it down the road. Whereas in gases, they're not as close together. They don't have as strong of interaction. So that kind of explains why sound is faster in solids than in gases. And liquids are in between. I couldn't really demonstrate that. I ran out of dominoes. All right, so a quick little summary here. All right, so sound is a longitudinal mechanical wave. Longitudinal means the particles move in the same direction as the wave. Parallel, we can say. Mechanical means it requires a medium. Okay, a sound wave is just alternating high and low pressure. Okay, that high pressure we call compression, the low pressure rarefaction. Okay, frequency is the pitch of the sound. Amplitude refers to the loudness. Speed of sound depends on the medium. So in general, we just looked at this. The speed in solids is greater than the speed in liquids, which is greater than the speed in a gas. Speed of sound in air depends on the temperature of that air. So we saw that the warmer the temperature, the faster that sound was. And it was given by that equation. Okay, we're going to wrap this up with a couple demos. The first one is something that maybe you've seen at your grandparents' house, and the second one you've probably never seen before, so check them out.
Okay, this is a record player. Maybe you've seen something like that in the past, or maybe you have one at home. Commonly, they're referred to as Victrolas. Now, Victrola is a trademark name from the Victor Talking Company. It's kind of like Xerox for a copy machine or Kleenex for tissues. But this one actually is a Victrola from the Victor Talking Machine Company. They were first made in the early 1900s, very early 1900s, and last made around in the 1920s sometime. So this particular one is from around 1920. But generally, it's basically a wind-up phonograph. So there's the crank there. You can just turn this to wind it up. And then there's a spring mechanism inside which will turn the turntable. So what's neat about this is there's no electricity, none. It just works on a spring. Now you can see the needle here. All right, so I'll get the turntable going. Just takes a few seconds to get up to speed. And then I'll put the needle on. And if the sound is too loud, you can turn down the volume just by doing this. It's not quite as loud, but that's the only volume adjustment there. So anyway, I mean, you guys have seen a record before. You know it has grooves in it, and the needle is sitting in a groove. And it's actually just one groove that spirals around all the way to the inside. But what happens, and I'm going to pick this up. Okay. What it is in those grooves, there's bumps in there. And then as the needle gets dragged across those bumps, it vibrates that needle. So this whole arm actually starts vibrating. And a vibration, creates that high and low pressure, that sound wave. And then that travels through the arm here and then down in here. And then somehow back in there, it's going to come out the speaker there. Okay, if we can call that a speaker. But that's it. I mean, sound is not that magical. You just need a source that vibrates to make that high and low pressure. And that's all a record is. Even the old, I'll say old, your parents' records, it's the exact same principle. It's just there, it makes an electric signal which goes to a speaker to vibrate the speaker. This doesn't have that. It's just all mechanical, just vibrates that, creates that alternating high and low pressure at the varying frequencies, and then out comes the music like that. So anyway, if you're interested, this is the album I was just playing, Glenn Miller, and then the song Blue Evening, if you want to pick that up on iTunes or something. But there it is. Very simple concept, but a 100-year-old machine still putting out good music. Okay, here's another demo. I have a plastic cup and then just this plastic strip coming out of the bottom. I tied a knot in there. Now listen to this. You guys hear that? I don't know how clear it's coming through, but it's saying happy birthday. And all I'm doing is I'm just dragging my thumb across this plastic strip. So now, knowing what you know about sound by now, you probably have guessed that there are grooves in this plastic strip. And I'm dragging my thumbnail across that. And these grooves are spaced just right that it's creating the vibrations in the plastic strip that are saying happy birthday. And those vibrations in the plastic strip go to the bottom of the cup, and that bottom of the cup goes in and out, creating that high pressure and low pressure. That's a sound wave. So again, these grooves are at just the right spacing to create that frequency to say happy birthday. Pretty cool.
Okay, that's it for the introduction to sound. I hope you learned some things, and I appreciate you watching it. As always, let me know if you have any questions.